it's the hardest to mess up. So it's not, the other ones work, but they're just easier to go wrong. So this is the one I recommend. And again, the reason I recommend that is because the current's the same. So there's no wrong current to plug into. And it allows us to very quickly see, for instance, that P is proportional to R, right? If I is the same, it tells us that the larger resistances do indeed dissipate the most power. Okay? All right? So let me kind of plan out this board so that I can add in the equivalent statements about capacitors. So let me put the capacitor equation on the top here. Capacitor. We, of course, have a relationship as well. I'm going to write it like this. I know it's a little bit of an odd way to write it, but it is just good old C equals Q over V, just kind of solved in this weird way. Actually, I should have put it like this. Q times 1 over C. And the reason I want to put it like that is because that makes it easier to compare the play-by-play with Ohm's law. So we have the voltage across the resistor. We have the voltage across the capacitor. We have the flow of charge through the resistor. We have the accumulation of charge on the capacitor, right? One allows charge to flow through, the other one just lets us pull up, right? And then we have the proportionality constant between those two things. Over here, that's the resistance. And over here, that's going to be 1 over the capacitance. Okay?
What did you say that was? Represent?
Oh, so the proportionality constant between them. So we said that if you increase the voltage, you're going to increase the current, and the thing that relates them exactly is the resistance. So I'm going to save myself a line so that I can write down a statement about the series capacitors. So leave a line blank here, and then I'm going to write down here my parallel stuff. And of course, right now, with the parallel stuff, I can go ahead and write down my resistor statement. For resistors, what's the same in parallel? Voltage. Voltage is the same, but the current is not. Okay? We actually find that the smaller resistors have the larger voltage, or sorry, larger current and power. Actually, do I want to say it like that? Let me phrase it opposite. Let me say the larger resistor gets smaller current and power. I had characterized that the large resistors are now the sideshow. So when you're talking about parallel, you have options. That's what parallel means, right? You have options. Now, the big resistor that you had to tussle with when you had a series and everything had to flow through there, now it's kind of the, oh yeah, that thing is over there, but most of the current goes through the easy way, right? So path of least resistance, as they said. So the larger resistor gets less current and also less power. So now all the action is on the small resistors. Before, all the action was at the large resistors. The bottlenecks now, all the action is at the small resistors. The larger resistance is relegated to a sideshow. And again, I suggested, not that the other ones are wrong, but I suggested, just in terms of making your life easy, to use that form of the power law for parallel. And again, the reason was purely functional. It's not that the other ones are wrong if you're careful with what you're doing. But since the voltage is the same for everybody, you can't really mess up on plugging that in. And looking at this, we can see that the power would be inversely proportional to the resistance, which indeed tells us that the larger resistances now have the smallest power. Okay? Now, the reason I'm doing all this, part of it is, of course, good recap on its own, but we're going to find that a lot of this stuff follows almost exactly analogously for capacitors, and it's nice to compare. For instance, I might as well, for the moment, put down my 3 equations for the potential energy storage on a capacitor. That was the one we started off with, and then we came up with 2 other forms. I'll put them in this order: 1/2 Q squared over C, and 1/2 CV squared. All right? So I've left myself space to put in the statements with series and parallel caps, and we're going to see how they're very, very similar. So I'm going to start with the easy one first, the parallel caps. Here's what I have. So I connect 2 capacitors in parallel across the battery. So basically the voltage drop is definitely going to be the same across them. So let's just go ahead and start off. I'll put the statements over here for capacitors. The voltage is, of course, going to be the same across them. We basically have one equipotential on top and the other one on the bottom. Now, I didn't bother to put in a resistor here, just because that would take this whole thing and make it an exponential, so that's not where the action is here. You can certainly combine it with that, but I want to basically say we get plus Q1 on this plate and minus Q1 on this plate, and likewise over here. So we're going to have positive charge flow to each of those things, and they're going to do that until both capacitors have the same voltage as the charging battery. Okay? So, they both have the same voltage, but they're not necessarily going to have the same amount of charge. So, let's compare. Well, I've purposely tried to represent in some graphical way that I want C2 to be bigger than C1. Now, of course, there's all sorts of reasons why capacitor 2 would be better than capacitor 1. It could have something to do with the dielectric or the plate area or the separation. Here, I've just literally tried to draw the plates looking bigger, having a larger surface area. So some way to easily visualize that this is a larger capacitor. Okay? That makes sense? Okay, so let's look at the formula. Q equals CV. If we have a fixed amount of voltage, we see that if the capacitance is larger, the charge stored will be larger. Okay? So, makes sense, right? We have 2 capacitors. We're charging them with the same voltage battery, but the bigger capacitor stores more charge. Okay? So we find that Q2 is going to be greater than Q1. If we want to make an analogous statement over here, we can say that the smaller capacitor stores a smaller amount of charge. Right? So I'm trying to make these line up, right? So I'm trying to make what is on the right side the same. So smaller current, smaller charge. So here it's the smaller capacitor that stores less charge, and the bigger capacitor that stores more charge. Okay? So how can we quantify this circuit if we wanted to talk about just how much capacitance is in it overall? So a C equivalent, right? A C equivalent, which has a charge plus Q total and minus Q total, like that. As the same way we did with resistors, with capacitors, we can choose to think of them individually or as a whole. And we can, of course, talk about Q total equals C equivalent times the battery EMF. So that's just applying the equation to the entire equivalent circuit instead of an individual element. Okay, so let's think about this. Well, oh, and the other thing before I even forget, let's do potential energy. So we'll look at potential energy. I guess we'll do 1/2 QV, let's say. So if we look at that, we already said that the V is fixed because they're in parallel. And we already figured out which one had more charge. So the one that has more charge will also store more energy. So all of the action is at the big capacitor. The big capacitor has more charge and it therefore stores more energy. Let's see if we can quantify exactly why. If we were to compare one charge carrier on this to one charge carrier on this, here's what we'd see. It's the same energy per charge. That's what voltage is, right? So if you compared a given charge carrier on each plate, you'd find it stores the same amount of energy. And that makes sense because they're both across the same voltage drop. This voltage drop across both is the same. The reason why the larger cap stores more energy is because you just have more of the charge carriers. You have more charges, each with the same energy. So of course, that's going to mean more overall energy. It's not that one electron on one plate stores more energy than one electron on the other one. It's that there are just more of them on one of them, okay? So you'll find some conceptual questions like that on the homework as well as on some of the practice exams, is not just figuring out if there's more energy on one versus the other, but why? Why is that? Is it because each charge carrier stores more energy, or because you just happen to have more of those charge carriers? So in this particular case, the reason why this capacitor stores more energy is because you have more of these charge carriers storing the same amount of energy as on the other one, okay? So that's your energy. And if we're going to finish this chart, we can again, here we're talking about the worst one, the smaller capacitor. It stores less charge and also stores less energy. All of the action is at the big capacitor. Okay? So, you can think of the small capacitor as like the sideshow, right? The small capacitor is a sideshow, not as much is going on with the small capacitor. All the action is at the big one, okay? Right? And by the way, this equation here was nice to kind of think through because you can think of both the amount of charge and the energy that each charge has. But I wouldn't recommend that one for general use. I would certainly recommend 1/2 CV squared. And I'd recommend it for exactly the same reasons. It's hard to mess up because V is the same for everybody. And so this is a way to very quickly see that the potential energy is directly proportional to capacitance. So that's a way to immediately see that the bigger cap stores more energy. So the bigger cap stores more energy. We don't have to go through the middleman of the charge if all we're interested in finding out is which one has more energy stored. If that's your interest, then just jump straight from C to PE, okay? That's why this formula exists. And by the way, notice the exact analogy here. In both cases, right, it's the voltage that's the same, so then it's nice because there's only one active ingredient in the formula, right? Here there's R, so you can see the direct relationship between P and R, because V is the same for everybody. Same thing here, right? V is the same for every one. So you can see very quickly what's the relationship between PE and C, right? Okay. Final order of business, we need to talk about how to calculate the equivalent capacitance. Well, my supposition is that I'm going to start with the total charge separation. The amount of charge we've separated, well, we've got Q1 plus Q2 on one side and Q1 and Q2 on the other side. The total amount of charge separation we've actually achieved with this rig is Q1 plus Q2. The way I like to think of this is really, this is kind of like one big parking lot. It has an artificial divider in it, right? You can't have that the charge goes willy-nilly from one top plate to the other top plate. But it's like one big parking lot with two entrances, right? You have one of those gigantic parking lots, two different ways to get in, that's fine. If you have some artificial weird divider in the middle of the parking lot where you can only go from one side to the other, or you can't cross from one side to the other, that's fine. It doesn't diminish how many cars you can fit in there, right? So that's what we have here. So essentially, we have two smaller capacitors acting in tandem as one big capacitor. And the charge separation we've been able to achieve is Q1 plus Q2. So let's go ahead now and throw in our equations. Q total is going to be C equivalent times the battery EMF. And then this one's going to be C1 V1. This is going to be C2 V2. And at this point, we realized, hey, actually, these are all the same voltage. And we find that this is a bigger capacitor. The equivalent function of two capacitors in parallel is one bigger capacitor. We just add their values. So we find that the addition rule when capacitors are in parallel looks like this. And of course, since it's a straight addition, that comes with all the mathematics conclusions thereof. Of course, the equivalent capacitance is more than any individual one. And if you have n identical capacitors of value C, then C equivalent will just be n times C. So I do want to point out here that the rules for addition here are, it's exactly the opposite. We used straight addition for series resistors, now we're using them for parallel caps, okay? The rules are actually reversed in both cases. That's jumping the gun a little bit, but the rules for series and resistors and parallel cap, so whatever you do for series resistors, you do for parallel caps. Whatever you do for parallel resistors, you do for series caps, okay? So you might think this is weird that everything is exactly reversed. I guess let me give you away the punchline. Why is everything reversed? Check this out. So everything is smaller over here. It's smaller for a larger resistor and a smaller capacitor. So large resistors are like small capacitors. The large resistor is the sideshow. In parallel, the small capacitor is the sideshow. I'll tell you why that is like that. Okay? Look at the rules. R is like 1 over C. Okay? So R, I don't know what the analogy symbol is. Some kind of colon thing, right? I don't know. R is like 1 over C. So a larger capacitor is like a smaller, larger resistors is like a smaller capacitor. They function in the same ways in a circuit. And in fact, that 1 over is exactly why the addition rules get flipped too. Okay? So if you have a good analogy or a good grasp of how resistors work, then you could almost just imagine instead of having two capacitors, you have two resistors, work out all your logic, and whichever thing is true for the larger resistor is true for the smaller capacitor. Okay? So they're highly analogous. We'll see everything is like that, in fact, we're ready at this point to, I think, do the series resistor, or series capacitors. Are there any questions before we do that? All right, so let's do that. So, series caps. So what if we had something like this? C1, C2. So, same deal. I'm going to have two capacitors in series. I'm going to have that one is bigger than the other. I'm going to ponder how I might think of their capacitance together as an equivalent. Among other things, I'm going to ask, of course, about the relative charge, about the relative potential energy, all that stuff. All right, so first let's piece together the flow. The way I like to think of this flow is like a relay race. So you will find that current flows here, putting a charge Q1 on here. Current goes like this, leaving behind a Q1 and putting Q2 here, and then continues forward and leaving behind minus Q2. This is all, of course, happening simultaneously. Remember that charge carriers pervade the system. So it's like, but if you think of it as like one charge leaving the battery, it passes the baton on to the middle leg, right? There's a runner in the middle that doesn't see the beginning or the end of the race. And then finally, over here, another charge flows into the low voltage terminal of the battery, okay? So first things first. When you have a relay race, somebody starts the starting line, passes it to someone who does the middle leg, and then passes the baton on to somebody who runs the middle leg, and then they pass the baton on to someone who finishes. It'd be really weird if the runner that started off with one baton and the runner that finished came in with 3 batons. Okay, something went wrong. Okay, there's a conservation of batons in your relay race. That is the same thing here. I will point out that this middle segment, okay, is not attached to the battery in any way. It is a plate and a plate connected by a wire, and they're not connected to anything else, right? So if that was neutral before, it better be neutral now, which means that this and this have to be the same amount. So we can conclude here that, in fact, the same amount of charge is stored across both capacitors. So if I add my statement over here, Q is the same. So notice, by the way, that I being the same and Q being the same in series is kind of like the same thing, right? I is the continued flow of charge, and Q is when the current has finished flowing, what it has deposited, right? What it has left behind, right? I is the flow of charge, and Q is the charge that got left behind, right? Does that make sense? So we go over here and take a look. Well, if Q is the same, how does that affect the voltage? So I'll solve for voltage. V equals Q over C. And Q is the same for everybody. So this tells us that it's actually the smaller capacitor that has a larger voltage drop. So if C2 is bigger than C1, then V2 will be less than V1. So we know in general in a series that you don't have to split the voltage drop up equally, and here we find that there's actually going to be more voltage drop across this one and this is smaller over here. So, let's talk about why that is. Well, this is like a tiny bad capacitor which you are cramming a bunch of charges onto in very close proximity, right? That is going to create a large charge buildup, okay? This is a much more casual, nice situation. These are your cage-free electrons, okay? They have room to roam. They're not crammed into a small pen. These are kind of spread out. They're not going to have as much of a voltage difference across them. That's why you see more voltage difference across the small capacitor, because that's the thing that's harder to store things on. You have to provide a larger motivation to get all those charges into a smaller space, right? We can go, of course, to energy. It's always instructive